Hello, everybody. I'll wait about 30 more seconds and then I'm going to start. Okay. So, why is this so zoomed in? Oh, I have to. Okay. So, hello, class. I hope you're all well. I'm going to start off with just a quick review of last time, where we were talking about stringed instruments. Okay, and what we found is that if you have a stringed instrument, because waves on a string are confined to go between one side and the other side, they create what are called standing waves. Okay, and you can't just have any standing wave on a string. They look a certain way. So we drew what they looked like. So I represented the string as being between two sides like this. And then there was a wave that looked like so. And so this was called the first harmonic. And the length of the instrument is L. And then I called this, I called this a, quote, football. And so to go to the next harmonic, you add a football. So now I have two footballs. All right, so that is the second harmonic. And then to go to the third harmonic, we do this. Like so. Okay, so now we have three footballs. All right, and it just goes on and on. So there are lots and lots of harmonics. Okay, so when you play a musical instrument, you're actually, when you pluck a stringed instrument, for example, you are actually creating a superposition of all of these harmonics. Okay, but usually it is the first harmonic that has the biggest amplitude. And I'll put parentheses usually. And so for that reason, when you play a musical instrument, typically it's the first harmonic of that instrument that you're actually identifying as the tone or the pitch that the instrument is playing. And then these other harmonics are present, but they basically give the sound its unique character. All right. So a standing wave like this, it has sort of like two important parts to it. So there are parts of the medium that are not vibrating at all. Okay. Such as these parts. So if you think about it, if the wave is doing this, the point where my fingers touch is not really moving very much. Okay. So those points where the wave is not moving very much at all are called nodes. Okay. And then in between two nodes, you have a point where it's where the medium is vibrating a whole lot. So for example, in the first harmonic, the center of the string is vibrating a whole lot. And so those spots on the medium where there's a whole lot of vibration occurring, those are called antinodes. Okay? So what we did is we looked at the length of the instrument, and then we saw how much of a wave was there in each case. Okay? And we used that information to determine the wavelength of the nth harmonic. Okay? And so the equation we came up with was that the wavelength of the nth harmonic is 2L over N. Okay? Now, of course, we don't usually visually see the harmonic, the wavelength, okay? We don't visually see that because the string is vibrating very rapidly. It's vibrating with a very small amplitude, so it's hard to even see the motion of the string. So what we do perceive is the tone. So what is the frequency of the nth harmonic? And so if we use V equals lambda F, we can determine the frequency. So we plug in for lambda and we solve for V or for F, and we get the frequency of the nth harmonic is NV over 2L. Okay? Where N is the harmonic number, L is the length of the vibrating portion of the string. Remember, when you play different notes on the same instrument, you move your finger around, which alters the length of the vibrating portion of the string. And then V is the speed of a wave on the string. Okay? So there are a lot of factors that affect the speed of a wave on the string. So factors affecting the speed of a wave on the string. So if I have my string, okay, there are a couple of things that can affect the wave speed on that string. So the first thing is, what is the string made out of, and how thick is the string? Okay, so you can have strings made out of nylon. You can have strings made out of steel. There are various materials. I don't know of any materials besides nylon and steel, but I presume that there are some. And furthermore, different strings have different thicknesses, and that affects the speed of a wave, because if the string is heavy versus light, it responds differently. So the density of the string has an effect. Okay. The other thing is that if I turn this peg here, it's going to change the tension in the string. Okay. And so more tension in the string will result in a higher wave speed, which will raise the frequency of the instrument. one of the interesting things about this is that actually tension or temperature, can have an influence on the tension in the string. So what happens is if the strings get cold, they tend to contract. Okay, so cold strings will tend to contract, and if you had a string that's pinned between two ends and it's trying to contract, you can imagine that what that will do is it'll increase the tension in the string. Okay, so the string contracts, it tries to contract, and that raises the tension. So if you have a cold string, it will tend to increase the tension, which will tend to increase the wave speed, and it'll make the frequency that the instrument plays go up. Okay, and so what that means is that if you take an instrument from a warm environment, a stringed instrument, from a warm environment to a cold environment, it's going to all of a sudden go sharp in response to that. So you always want to tune your instrument in the environment that it's going to be played in. Okay. The other thing is even moisture content can affect the wave speed. So, for example, if you have a guitar and you take it to a very humid environment, well, the wood in the guitar is going to absorb some of the moisture from the air. And when wood absorbs moisture, it expands. So what happens is, if I take this ukulele to a really moist environment, really humid air, it's going to absorb some of the moisture. The wood will expand, which will stretch the string more, and again make it go sharp. Same thing happens with pianos. So if you get a piano and they bring it to your house, probably you're not doing it yourself because they're really heavy, but if you bring it to your house, they're going to recommend that you don't tune the instrument for a while, because what you want to do is you want to let the instrument reach the same temperature as the environment. You want to let the instrument absorb moisture or dry out so that it's matching the humidity of the environment. And so they recommend waiting a while before having it tuned. If you just had it tuned the same day that it was brought in, it's going to be out of tune very shortly after that. There's a question: can a cold string also increase density? It would. I believe that effect is less significant than the effect of the string contracting. But yeah, if you cool something down, it contracts slightly, which does increase the density. But I think that is less significant than the increase in tension. Okay, so for stringed instruments, I will tend to call those closed instruments. All right, and the reason I call them a closed is because they have nodes at each end. Okay, let's go ahead and do an example, just because we didn't do any yesterday. These equations are pretty simple, but we'll just do an example. So let's suppose that we have a stringed instrument is 0.6 meters long. The wave speed on the string is 530 meters per second. Calculate the frequency and draw the 7th harmonic. Okay, Now, of course, the 7th harmonic is not going to be the one that you hear, most likely. So you're most likely going to hear the 1st harmonic, but that is going to be present in this superposition when you pluck the string, and it's going to add to the qualities of that particular instrument. So we want the frequency of the 7th harmonic, which would be 7V over 2L. All right. And then so we would have 7 times the wave speed is 530 over 2 times the length of the instrument, which is 0.6. All right. So if you work that out, you get 3092 hertz. Okay. And then, of course, it also says to draw the 7th harmonic. And so remember, harmonic number is related to the number of footballs. Okay, so we can see that the 1st harmonic has 1 football, the 2nd harmonic has 2 footballs, the 3rd harmonic has 3 footballs, etc. Okay, so the 7th harmonic is going to have 7 footballs. So I'll draw 7 footballs. 1, 2, 3, 4, 5, 6, 7. And here are the ends of the instrument. Okay. 1, 2, 3, 4, 5, 6, 7. Okay. So that is what the 7th harmonic would look like. So it's a pretty complicated wave. All right, so now we're going to get to the new content for today. And today we are talking about wind instruments. All right, so wind instruments are typically a tube that air is vibrating in. Okay, so if we imagine looking at a tube from the side, this is my picture of a tube from the side. Okay, so this is what I would call an open instrument, because both ends of the tube are open to the environment. Okay, but you can also have what's called an open closed instrument. So an open closed is just a tube that is capped at one end. Okay, so these are both possibilities for wind instruments. We don't talk about a closed open because, you know, if you take an instrument that looks like open closed and then you flip it and view it from the other side, now it's closed open. Okay, so it's the same thing, just from a different perspective. All right, so we're going to start off by talking about open instruments. All right, and so open instruments have, instead of a node at each end like a string, open instruments actually have an antinode. They have antinodes at each end. So let's go through and let's draw. So the first harmonic is going to be the simplest wave that you could make that has an antinode at each end. Okay, and so it ends up looking like this, kind of like an hourglass. Okay, so that is the first harmonic. Now, how do you go to the next harmonic? All right, and so as I said earlier, to go to the next harmonic, you always add a football. You can't add a football to the end because it would be weird if you had a wave that kind of looks like this and then has a football tacked on at the end. Okay, that's just weird. So what you do is you add the football in the middle for open instruments. So the next harmonic is going to look like this. Okay. So this is the first harmonic. This is the second harmonic. And to go to the third harmonic, I will add a football in the middle. Okay, so there's the third harmonic. And then finally, I could draw more, but I'm going to stop after the fourth harmonic. So that's going to, again, add a football in the middle. Boom. Okay, so it looks like that. So if the length of the instrument is L, okay, we could go through and we could do the exact same analysis we did last time. We could try to identify how much of a wave is this. It turns out that this right here is half a wave. Okay, why? Because we have half of a crest and half of a trough. So to finish the wave, we need the other half of the trough, and we need the other half of the crest. Okay, so that means that the wavelength of this harmonic is 2L. Okay, here we have half of a crest, a full trough, and then here's the other half of the crest. All right, so this is a full wave. So here we have the wavelength is L, which is 2L over 2. Here we have a full, or half of a crest, a full trough, and then half of a crest. All right, so this is 2/3 of the total length of the instrument. So the wavelength of this harmonic is 2L over 3. So hopefully you can see that it is actually, for open instruments, it is actually the exact same formula. So the wavelength of the nth harmonic is 2L over n. Okay? That being said, so then we can go ahead and use V equals lambda F, and we can solve for the frequency. We get the frequency of the nth harmonic is NV over 2L. Exact same formula. There is an important difference, though, in the interpretation of V. Okay? So what is the medium that is vibrating in the case of a wind instrument? In a wind instrument, it is the air inside the instrument that is doing the vibrating to produce the sound. Okay? Excuse me. The air itself is vibrating. So V is the speed of the medium that is doing the vibrating. Okay? So instead of being the speed of a wave on a string, like for a closed instrument, this is going to be the speed of sound of the gas that is filling the instrument. Okay? Which is probably air. It doesn't have to be air. But if it is air, then the speed is around 340 meters per second, depending on temperature, humidity, and other variables. So, yeah, if you've ever slurped helium before, I'm sure you all have at a birthday party or something like that. You slurp helium and your voice gets higher. Well, why is that? It's because helium is a lighter gas than air. Helium is, atomic number 2. It's one of the lightest gases. Okay, and so because it is such a light gas, its wave speed is very high. Okay, so helium has a very high wave speed, and so the increase in wave speed makes the frequency higher, which makes your voice high-pitched when you speak with helium in your lungs. Okay. I want to talk about the effect of temperature. So temperature affects the speed of sound. Okay. Hotter air, sound waves travel faster in warm air than in cold air. Okay. So what that means is if you tune a wind instrument in warm air, okay, and then you take it outside to cold air, the speed of sound is going to drop from where you were compared to where you are currently, and that's going to make your instrument go out of tune. Okay, so it's going to make the frequencies go down. So it's kind of interesting because in wind instruments, because if you take it into a cold environment, the speed of sound drops. That lowers the frequency. So wind instruments will go flat in a cold environment. Whereas stringed instruments, you take it into a cold environment, the strings contract, which makes more tension in the string, which raises the pitch of a stringed instrument. So if you take a stringed instrument into a cold environment, its frequencies go up. It goes sharp. So different types of instruments change in different ways when they're taken into new environments. Another interesting thing about wind instruments is that they need to be warmed up. Okay, if your instrument is cold, it's going to cool the air inside it. Okay, and as the instrument itself warms up, it will warm up the air inside it, and so the instrument needs to be played a little bit. It needs to be warmed up until it reaches a consistent temperature, and then you tune it. Okay, so you wouldn't want to just pull it out of the box and then immediately tune it, or you could, sort of pre-tune it and then make a minor adjustment if you wanted to. But I don't know. I don't play any wind instruments, so I don't know how that works. Maybe someone can tell me later on in the Zoom room. So let's do an example. Suppose that an open instrument is 0.35 meters long and filled with air. Okay. You play the instrument. What frequency is heard? Okay. So obviously 0.35, that is L. The fact that I said it's filled with air, that is telling you basically what medium it is and therefore the speed of sound. So if we're talking about air, the speed of sound is 340 meters per second. We don't know what the temperature is, so we won't worry about that. You play the instrument, what frequency is heard? So in the absence of additional information, we have to assume that it is the first harmonic that we are going to hear, because usually that has the biggest amplitude. Okay? So frequency of the first harmonic is going to be 1V over 2L, 1 times 340 over 2 times 0.35, which is 486 hertz. So there you have it. So the last instrument we need to talk about is open-closed instruments. Okay, so open-closed instruments, they're going to have an antinode on the open end, and they're going to have a node on the closed end. Okay, this is actually more realistic than an open instrument. So I don't know of any wind instruments that are truly open, but there are a lot of wind instruments that are closed, or open-closed, excuse me. So for example, a flute is capped at one end, and then it is open at the other end. Horns have the horn end, and then the part where your mouth goes is very narrow to the point that it's basically closed. Okay. So wind instruments are more often open-closed than open. Okay, so I draw that like so. So this is representing the closed end. So on the closed end, we have to have, and the length of the instrument is L. So on the closed end, we have to have a node. Okay, so, and then on the open end, we have to have an antinode. And we have to go between them with the simplest possible wave, and that is the first harmonic. Okay, so the simplest wave you can draw that has a node at one side and an antinode at the other side is one that looks like this kind of. It's such a small portion of a wave that it almost doesn't look like a wave, but it is. So what this is right here is half of a crest. Okay, half of a crest. So if we want to know what is the wavelength of this harmonic, we had better draw a full wave. Okay, so we can see that to get a full wave, I have to have the additional other half of the crest. I have to have half of a trough, and then I have to have the other half of the trough, and that's a full wave. So if we have, so if this distance right here is L, then the other half of the crest is also a distance L, and half of a trough has a distance L, and then the other half of the trough has another distance L. So the total length of this wave, even though we don't have a full wave, if we were to extend it to an entire wave, its wavelength would be 4L, which I'm going to write in the suggestive form of 4L over 1. Okay. To go to the next harmonic, you always add a football. Okay, so I'm going to add a football to the right or to the left side of the wave. So like that. Okay, so what I like about the crests and the troughs is they kind of naturally divide up the instrument. Okay, so like this is dividing the instrument up into 3 segments in my mind. Okay, now if I wanted to complete the wave, I have a full crest, but I only have half a trough, so I would have to add the other half of the trough to make a full wave. Okay, and so we can see that if this is L, then this is L over 3, this is L over 3, and this is L over 3, because the wave naturally divided the instrument up into 3 parts. And then to finish the wave, we have an additional L over 3 to go. So how many L over 3s do I have? I have 4 of them. And so the wavelength is going to be 4L over 3. Now, because the denominator is 3 and not 2, this is called the third harmonic. So there is no n equals 2 harmonic for open-closed instruments. Okay, there is none. So now we go to the next harmonic, so I add another football in. Okay, so I like to think about this as dividing the instrument up into segments, each segment being half of a crest or half of a trough. Okay, and so because I've divided it up into 1, 2, 3, 4, 5 segments, each one of these is L over 5. Okay, and a full wave has a full crest and a full trough, so it's going to include these 4 segments is a full wave. All right, so that means that the wavelength of this harmonic is 4L over 5. So for that reason, this is called the 5th harmonic. Okay, and I'll draw one more. Just like that. Okay, and this would divide it up into 7 parts. That are supposed to all have the same size, and we need 4 of those parts to get a complete wave. So the wavelength of this harmonic is 4L over 7. So I think at this point we have established a pattern, and you can see that the wavelength of the nth harmonic is 4L over n. But the restriction is that we don't have a 4th harmonic, we don't have a 2nd harmonic, we don't have a 6th harmonic. So clearly n must be an odd number. Okay? Then of course we can use V equals lambda f, and so we can determine the frequency of the nth harmonic. Frequency of the nth harmonic is NV over 4L. Okay? So these are the two equations for an open-closed instrument. So there's just a slight difference in that the equation has a 4 instead of a 2. All right? And then the other difference is that you can only have odd harmonics for open-closed instruments. So if I asked you something like, what is the frequency of the, 12th harmonic of this open-closed instrument, you would say it doesn't exist, okay, because 12 is an even number. All right? So, one thing I want to say is this is for what we've studied here are musical instruments, but we've studied one-dimensional musical instruments. So a tube is essentially one-dimensional, okay? If you're inside a tube, you can go forward and backwards only, all right? A string is one-dimensional. So we're studying one-dimensional instruments. There are other instruments that are inherently two-dimensional, okay? So for example, a drum. Drums have a drum head, and you can walk in 2 directions along the drum head, okay? So drum heads, you could think about it as having a node along the outside, along the outer rim of the drum, because the drum is tied down at that along the outer edge. But because it's two-dimensional, it has a lot more complicated frequencies. Okay, so in fact, a drum head, because it's two-dimensional, it has 2 harmonic numbers. So there's a lot more harmonics for drum heads, and that's the reason why drums don't really have a tone, or it's very difficult to sort of get a tone on a drum. You know, if someone plays a drum, you're not like, aha, that was 500 hertz. Okay, it just sounds like, you know, a beat essentially. And the reason for that is because drums have a lot more harmonic frequencies that make it, and they're all crowded together. And so it makes it harder to perceive a single harmonic as being the strongest harmonic and having a tone, okay? So in order to perceive a tone, one of your harmonics needs to be bigger than the rest in order to single it out as being the tonality of that particular instrument. We're going to talk a little bit more about this in the Zoom room, but that's all I